Hello everyone. Today I'm going to discuss on unsymmetrical fault calculation. Myself Sudhanshu Sarkar, Assistant Professor, Department of Electrical Engineering, Narula Institute of Technology. So this is the first lecture. So in today's lecture I'm going to discuss with all of you the four important topics on unsymmetrical fault calculations. The first one is unsymmetrical faults on three-phase system. So we will go through the definition and explanation, and the second one is symmetrical components method and the explanation of symmetrical component methods, and the third one is the most important one, that is operator A. So we'll try to understand that what is operator A and how we can use this operator A for unsymmetrical fault calculations. And the last topic will be covered which is symmetrical components in terms of phase currents. Now moving to the next slide. So here the definition is given about unsymmetrical faults on three-phase system. So what is actually these unsymmetrical faults on three-phase system? Let's start with that. Those faults on the power system which give rise to unsymmetrical fault currents are known as unsymmetrical faults. So it's a very simple definition. And the next one, we are going to discuss on unsymmetrical faults on three-phase system and the explanation of this. So we already discussed on the definition of unsymmetrical faults. Now there are three ways in which unsymmetrical faults may occur in power system. The first one is single line to ground fault, that is represented with LG, and the diagram of single line to ground fault is in figure 1. So here we have three phase R, Y, B. So if the fault is with any phase, then it is called single line to ground fault. Here it is shown that the line ground fault is with B. You can show it with Y and or with R. So if any phase on the ground, if the fault is there, then it is called line to ground fault. Second one is line to line fault, that will be represented with LL. So this is the diagram for line to line fault. So here it is showing that here is a fault between Y and B. So if we show that line between R, Y, that is also correct, and if the fault in between R and B, that will be also correct. The third one is double line to ground fault. So double line means LLG will be the representation of double line to ground fault. So here R, Y, B phase, and it is showing that the fault is between YB phase and with the ground. So these three types of fault we'll find in the power system for unsymmetrical fault calculation. So first one is single line to ground fault, second one is line to line fault, and the third one is double line to ground fault. Now the most important part of this chapter is symmetrical components method. So what is this symmetrical components method? Look, any unbalanced system of three-phase currents or voltage may be regarded as being composed of three separate sets of balanced vector. So currents or voltage may be regarded as being composed of three separate sets of balanced vector. So term is very important, balanced. What is balanced? So balanced system or balanced vector means if all the phase, the magnitude of all the phase are same and the distance between them is 120 degree. So that type of system is called the balanced system. So what are the three types? So three types. The first one is positive. In number 1 you can see that first one is positive phase sequence component, second one is negative phase sequence component, and third one is zero phase sequence components. So Now the question is, what is positive phase sequence component? A balanced system of three-phase current having positive phase sequence is called positive phase sequence. So positive phase sequence is also called normal phase sequence. That means a balanced system should be balanced. That means the magnitude of R by B will be same, and the angle between these three phases is 120 degree. So a balanced system of three phase currents having positive, or positive means the normal phase sequence. Now number 2, negative phase sequence components. A balanced system of three currents having the opposite or negative phase sequence. So the first one is positive, and for negative it is negative. Negative means the opposite. So if the currents having opposite and negative, then it is called negative phase sequence. And the last one is the zero phase sequence components. A system of three currents equal in magnitude having zero phase displacement. That means there will be no displacement of the phases. In the first two cases, the displacement was 120 degree, but in this case there is no displacement. The displacement is zero, and the magnitude of all the three currents will be equals. That means for zero phase sequence component, it will be parallel. So here, the first one, a balanced system of three phase currents, IR1, IY1 and IB1 having positive phase sequence. So as in figure, we can see that it is a RYB phase sequence. It is shown in figure number 1. These are positive phase sequence components. And try to remember, if the subscript is 1, that means here you will find that IR1, IY1 and IB1. That means 1 is actually represent normal of or positive phase sequence components. So here it is showing that the phase sequence is RYB, and this is called positive phase sequence. So if you follow very carefully, you can find that we have three phases, R phase, B phase and Y phase, and the direction is given anti-clockwise. So here all the phase is same, the magnitude, that means the magnitude is same, and the angle between each phase is 120 degree. That means it's a balanced system. So why it is called RYB? Why it is not RBY? Look, here the direction is showing anti-clockwise. So this is IR1, this is IY1, this is IB1. So sometime you may think that why it is not RBY, why it is RYB. Look, to understand this process, you have to understand something more. What is that? Look, suppose you are sitting here in this position on the top. So if your position is fixed and you are sitting on a chair and the system is rotating anti-clockwise, then what you will see first? First, you will find R phase is moving. Then we will come next Y phase, and after that B phase. So IR, IY, IB. Your position should be fixed and the phase will rotate in anti-clockwise direction. Then who will come first? IR, then Y, then B. So for that reason it is called RYB, and this RYB phase sequence is called positive phase sequence. The next one is negative phase sequence. In figure 2, follow very carefully. For negative phase sequence, the sequence is represented with IR2, then IB2, IY2. The concept is same. So you are here and the phases is rotating anti-clockwise. Then what will happen? Will come first. IR2 will come first, then will come next B phase, and after that Y phase. So the phase sequence for negative phase sequence will be RBY. It is written here RBY. And look, For positive phase sequence, the subscript was 1, IR1, IY1, IB1, but here the subscript is 2. That means if somewhere is written 2, that means it is actually showing negative phase sequence. Next is the last one, third one, that is the zero phase sequence. So for this zero phase sequence, we know that it is represented with 0. So for positive 1, negative 2, and for 0, 0. So three currents IR0, I10 and IB0 is equal in magnitude and zero phase displacement from each other as shown in figure 3. There are the zero phase sequence components. So this is the diagram for zero phase sequence component. So the next one is very important. So from the last concept, what we can understand that the current in any phase is equal to the vector sum of positive, negative and zero phase sequence current in that phase as shown in below figure. So what is actually this? Look, we have three phases, R, B and R, Y and B. So in R phase, the total current is IR. But look, the phase is equal. The current in phase is equal to the vector sum of positive, negative and zero phase sequence. That means IR has three phase sequence. What is that? IR1 positive, IR2 negative, IR0 zero phase sequence. So IR current, the current in any phase is equal to the vector sum of positive, negative and zero phase sequence. So IR equals to IR1 plus IR2 plus IR0. In the same way, IY will be equals to IY1 plus IY2 plus IY0. And for B phase, the concept is same. IB equals to positive phase sequence of B, negative phase sequence of B and the summation of zero phase sequence. So for this concept, we can write these three equations. The next topic is operator A. So what is operator A? It's a very simple and easy concept we have to use to calculate the unsymmetrical fault calculations. So it has a vital role, the operator A. The operator A is 1, which when multiplied to a vector rotates the vector through 120 degree in the anticlockwise direction. That means if we multiply A operator with any vector, then what will happen? That particular vector will rotate anticlockwise. So what will be the rotation? It will be 120 degree. Now let's discuss on it. Look the figure. The figure here we have three vector, vector A, vector B and vector C. So in vector A, the current is I. Look, consider vector I represents by OA as shown below. No, it's actually shown above. So the vector OA is representing along OA, the vector is I. If the vector is multiplied by A, so from the definition we can say that if we multiply operator A with I, then what will happen? If the vector is multiplied by operator A, the vector is rotated through 120 degree in the anticlockwise direction. Okay, so if we multiply A with this, then it will, the OA vector or I current phasor will rotate 120 degree along the anticlockwise direction. That means if we multiply I by A, then what will happen? It will rotate anticlockwise 120 degree. It is shown here. So the next now position is AI. So and the position is OB. So it is OB. So AI equals to I into 120 degree. That means I into cos 120 degree plus J sin 120 degree. And now put the value and finally we'll get A equals to minus 0.5 plus J 0.6. Now again if we multiply, go to the last slide, OB vector by A, then what will happen? We'll find this OB vector again rotate 120 degree in anti-clockwise direction and the next position will be A square I. Okay, so and it is represented by OC. So it is written here and the same way we can calculate the value. If the vector assuming position OB is multiplied by operator A, OB multiplied by operator A, then it will rotate 120 degree anti-clockwise. The next position is OC. Look, it is OC actually, and A square I, that means I angle 240 degree from the first position. So after putting the value of cos 240 degree plus sin 240 degree, the A square value will be equals to minus 0.5 minus j 0.06. Similarly, we can find A cube. A cube means if we rotate the value OC, if we multiply OC again with A, then it will be A cube, and putting all the values of cos 360 degree plus j sin 360 degree, because if we rotate OC again 120 degree, then it is actually rotating 360 degrees. So putting all the value, we'll finally get the value A cube equals to 1. So from here we can conclude some relation of A square, A cube, and using the value we can calculate the next topic. The next topic is symmetrical components in terms of phase currents. Look, the unbalanced phase currents in a three-phase system can be expressed in terms of symmetrical components as under. So here IR equals to, we already find that how it is coming, how the equation is forming. IR equals to IR1 plus IR2 plus IR0. In the same way IB and IC, IB and IY. So look, these three figure we already discussed on it. So let's follow the first figure very carefully. What is here? It's positive or negative phase sequence. IR, IY, IB, 1 1 1. That means it's positive phase sequence. So positive phase sequence, this phase is IR1. Now we already learned what is operator A. So if we multiply IR1 by A, then what will happen? This phase will rotate 120 degree, and the next position will be IB1. That is equals to IB1 equals to IR1 into A. And then if again we multiply A with IB, then what will happen? I by 1 will be equals to A square IR1. So in this way we can represent all the phasor with IR phasor. So the second phasor, if you follow carefully, you can find or you can understand the same way. For negative phase sequence IR2, we multiply A with IR2. Next position is I by 2. So and the third one is IB2 equals to A square IR2. So what is actually happening here? We are converting all the phases in R phase, and here we don't have to do anything else. So look, it's clear from the above figure that IR1 equals to IR equals to IR1 IR2 plus IR0. So first one, there is no doubt. Now we are converting IY with IR. So look, for third figure, IR0 equals to IY0 equals to IB0, because all the magnitude is same for all these three phase for third figure. So look, the calculation IR, we don't have any problem with IR, because IR equals to IR1 plus IR2 plus IR0, and IY equals to IY1 plus IY2 plus IY0. But here we have to put the value from the above figure. Look, so what is IY? IY1. So what is IY1? Look, IY1 is here. It is IY1 A square IR1. So put it here, A square IR1. Next IY2. From here we can find IY2. So A IR2. Put here A IR2 plus IR0. IY0 equals to IR0 from third. And in the same way B, we can convert the B phasor. We have to convert it from B to R, red phase. So IB1, from here IB1 equals to A IR1, and then IB2 equals to A square IR2, and IB0 equals to IR0. No doubt about this. So in this way we can form these three equation. IR is representing with R, IY is also representing with R phasor, and IB is also representing with R phasor. Next, so we are going to find the zero sequence current. By adding expression 1, 2 and 3, we have IR1. So we are adding actually equation 1, 2 and 3. So IR1 plus IR2 plus IR plus IY plus IB. So put from this three equation, just add this three equation, IR plus IY plus IB, that is equals to IR. So IR is here in all the equation, IR1, IR1. So 1 plus A square plus A. Next IR2. So here it is also IR2 into 1 plus A square. And here IR, that means 3 IR0. IR plus IR0. So IR equals to 1 plus A square plus A. IR2 equals to 1 plus A square plus 3 IR0. So 1 plus A square plus A. So you already find the value of A and A square. So if we add 1 plus A square plus A from operator A calculation, we'll get that should be equals to 0. Also this is equals to 0. So what is the value finally we are getting? That is, after putting all the value, we'll find that IR plus IY plus IB equals to 3 IR0. That means IR0 equals to 1 by 3 IR plus IY plus IB. As the rate phase is always taken as the reference phase, therefore subscript R is usually omitted. So the phase sequence component I0 equals to 0 phase sequence. This is 0 sequence current. So 0 sequence current is equals to 1 by 3 of IR plus IY plus IB. So similarly, or in this way, we can find the value of positive sequence current. So what we have to do for positive phase sequence current? Multiplying expression 2 by A and expression 3 by A square, and then adding these expression to expression 1 we get. So what we have to do? Multiplying equation 2, that means this is the equation, multiplying equation 2 by A and 3 by A square, multiplying equation 2 by A and 3 by A square. So we have to multiply A and this is A square, and then we need to add these three equations. So what will happen? IR plus A, IY plus A square IB. So after putting all the value, because A cube, we already proved that A cube goes to 1, A plus A square plus A to the power 4. A to the power 4 means A, so A plus 1 plus A square equals to 0. Here it is 0, so finally we are getting 3 IR1. So IR1 equals to 1/3 of IR plus A IY plus A square IB. Omitting the subscript R, we find I1. That means the component current 1 means the positive sequence current equals to 1/3 IR plus AIY plus A square IB. So similarly, we can find the negative sequence current. So what we have to do? Multiplying expression 2 by A square and then 3 by A. So in the previous case for positive, we multiply 2 by A and 3 by A square, and then adding 1 to 3, we find positive phase sequence. And here A square with 2 and A with 3, then IR plus A square IY plus AIB. So after putting all the value, we find because 1 plus A square plus A to the power 4 equals to A cube into A. So A cube equals to 1, that means A to the 4 equals to A. So 1 plus A square is 0. Again 1 plus A square equals to 0. And here 1 plus A cube, that means 1 plus 1 plus 1. So 3. So 3 IR2. So the negative IR2 equals to 1/3 of IR plus A square IY plus AIB. So I2, we are omitting here R because this is the reference phase. So I2 equals to 1/3 of 1 by R plus A square IY plus AIB. So this is the calculation of A. It is showing here. So now I am going to, and for this making PowerPoint presentation, I take help from the Principle of Power System by V.K. Mehta and Rohit Mehta. Thanks to all for watching. Goodbye.